Hello everyone, this is me Syed Waqasul Haq and I am here making this video for presenting my research paper topic on microfluidics and its application of electronics thermal management. This presentation is submitted to Professor Dr. Zhang in partial fulfillment of the requirements for ELG 7132 course of Nanoelectronics. So let's get started with the contents of this presentation. In this presentation, I will be discussing about motivation, introduction, working of a microfluidic chip, advantages, application of a microfluidic devices, solutions, methods, microfluidic heat sink, microfluidic pump, micro air cooler, what's next, and conclusions. So let's talk about the motivation. The manipulation of fluids in the channel with the dimension of tens of micrometers, microfluidics has emerged as a distinct new field. Microfluidics has the potential to influence subject areas from chemical synthesis and biological analysis to optics and information technology. But this field has the potential to outgrow the nanotechnology if it's worked in the right direction. Introduction. So let's get started with the introduction. So, a microfluidics is a technology that precisely deals with performance, the controlling, and the influence of those types of fluids that are generally very small in size, usually around the microscale, the nanoscale, picoscale, and the femtoliter scale. By the dimension, the size of these fluids is around 10 to the power minus 6 to 10 to the power minus 12. The way these fluids behave is very different as compared to the fluids in our daily life. These microfluids are very smaller in size with respect to its volume, considering that it actually goes down to the scale of femtoliter, that's 10 to the power minus 12. This femtoliter scale of the fluids are general in quadrillion time of a daily use liter scale, which by the comparison is very small. This is why these unique features involved in microfluidic is reforming the shape of newest technologies and is proving to be the key in newest experiments and the modern innovations. More about the working of these microfluids we are going to discuss in how microfluidics work. But the basic operation of these microfluidics is to shorten the size and make a system micro-sized so that it could fit in it a size of whole laboratory. The science behind this technology is that it's based on the flowing of liquid, which is through the concise channel that consists of chambers and narrow tunnels from which the fluids are flown. Now let's talk about the working of a microfluidics chip. A microfluidic chip is a pattern of microchannel molded or engraved. This network of microchannels are incorporated into a microfluidic chip that is linked to the microenvironment by several holes of different dimension hollowed out through the chip. It is through these pathways that fluids are injected and evacuated from the microfluidic chip. Fluids are directed, mixed, separated, or manipulated to attain multiplexing, automation, the higher throughput system. These microfluidic channels must be precisely elaborated to achieve the desired features. Here are some examples of the microfluidic chips that includes a channel that is thinner than 1 nanometer and an example of a lab on a chip of a microfluidic device. Now let's talk about the advantages. Advantages of microfluidics are that they help in decreasing the sample and reagent consumption in an experiment. This is by improving the precision of the task. The other advantage of the microfluidics is that they help in achieving the task quickly by shortening the experiment time period. The third advantage of microfluidics is that they help in decreasing the overall cost of the experiment by running many simultaneous tasks at the same time. And the last advantage of microfluidics is they help in reducing the size of the devices. Now let's talk about the application of microfluidic devices. Due to the miniaturization, the integrated circuits having a transistor are scaling down lower to lower due to the fact of that the number of transistors are getting increased on a chip day by day. Considering that as an asset, we also have to keep that in mind that due to this level of high transistor on a chip, it's causing a lot of power issues. This is not it. Maybe in the future, due to the use of higher consumption of commercialized wide bandgaps semiconductors such as GaN, the chips may suffer even more power issues. This may result in the heat flux enlargement on a chip devices. These days, 3D stacking is also very popular, and this popularity of 3D stacking can lead to even worse scenario for the thermal issues. Now, keeping these issues in mind, we have to think that this thermal problem is gradually becoming the bottleneck that may restrict further innovation in the field of the nanotechnology. We can see in a figure that the thermal management is a critical for fast developing electronics. There is a chip that has a lot of transistor on it that has a thermal issue. That flux is represented in this whole diagram. That thermal flux is rising sharply, which is due to the fact that the device sizes is scaling down due to the 3D integrations that result in thermal management, which is very critical. So the whole purpose that we have to take care of the thermal management issue seriously is that so we can reduce the flux that has been rising very sharply. There are solutions for this thermal management like conventional forced air coolers, liquid cooling, or maybe heated pipes, but these solutions may not be strong enough to overcome the challenges regarding the thermal management. Now let's talk about the solutions. The solution is obviously the microfluidic devices. A microfluidic device displays a great probable in the thermal management of an electronic devices. The channel inside the chamber of microfluidic devices could be manufactured with monolithic substrate with the integrated chips. The provided coolant liquid can be flown from a microfluidic chamber. This process can openly remove the heat from the surrounding areas. The above prescribed procedure could have the ability to minimize the path of the heat that flows right through the heatsink. This helps substantially decreasing the heat dissipation efficiency. With that, we can also integrate the microfluidic devices in between the stacked chips. This will result in relaxation in the thermal heat issue in 3D integrated chips. Now let's talk about the methods. There are three main basic methods for managing the thermal issues in an electronic devices: micro air cooler, microfluidic pump, and microfluidic sink. So here we will be starting with microfluidic heatsink. So mainly in a microfluidic device, there are three main components, that is the integrated power circuit, two chips, namely chip A and chip B, and a platinum thin film coil, that's PT. Through the process of microprocessing, the chip A and chip B are being fabricated. For the heat source, we use that platinum coil that also acts as a stimulated power integrated circuit. For the microfluidic channel, we use the chip A, which contains the 50 fluidic channels that are straight, and each of that channel has a dimension of 50 micrometer. The heat from the integrated power circuit is removed when the coolant is flown from the micro channel. A PT coil are fabricated to the chip B. It corresponds to the centrally fluidic channel. Here in a cross-sectional picture illustrated that the two temperature sensors, namely S1 and S2, are placed at inlet and outlet at the heatsink respectively. The 9 temperature sensors, denoted from S1 to S9, are equally distributed in the central fluidic channel with a pitch of 500 micrometer. This configuration ensures that the temperature profile in the fluidic channel can be extracted. Thin film-based resistor is employed as a temperature sensor because of its high sensitivity and stability. The temperature coefficient of the resistance of the annealed PT thin film remains stable at the elevated temperature. To precisely measure the resistance of the temperature, all sensors are wired connected, eliminating the effect of parasitic resistance of the connection wires. Here, this schematic graph provides the temperature data acquired by the embedded thin film sensor. It is shown when the temperature rapidly drops from 72 to 35 degrees centigrade, when the coolant is turned out, indicating that the coolant is efficiently managing the thermal issue inside the device. Now let's talk about the microfluidic pump. The liquid coolant in the microfluidic heatsink is driven by the microfluidic pump. Since its the heat dissipation capability is proportional to the flow rate, a powerful microfluidic pump is highly demanded to realize desired cooling capability. Unfortunately, because of the backflow effect of the valveless microfluidic pump, the net output flow rate of the valveless microfluidic pump is far from satisfaction, even after decades of development. As shown in the figure, the 3D schematic drawing of an innovative valveless microfluidic pump, the simulation result of the fluid structure interaction, is shown in figure 5b, where the yellow arrow indicates the flowing direction of the fluid. As shown in the figure, when the microfluidic pump is under the sucking phase, the fluid flows from both inlet and outlet into the pump chamber. When fluid flows from the inlet to the pump chamber, the diffuser and pump chamber are equal to the two diffuser connection. The fluid encounters a small resistance. At the same time, when the fluid flows from the outlet to the pump chamber, the nozzle and pump chamber equals to that nozzle connects with a large angle diffuser. The velocity of fluid increases along the nozzle section and reaches the large value in the end to the nozzle. Due to the diffuser angle, which equals to 180 degree, it locates the jet flow region, and high velocity fluid generates turbulence in this region. The normalized net flow rate with the time is illustrated in 5c. The pump net flow rate is always positive, indicating that the backflow is largely suppressed. A considerably high flow rate of 5 ml per minute is achieved. Now let's talk about the micro air cooler. The heat taken from the IC by the microfluidic heatsink needs to be eventually dissipated to the environment. Passive heat dissipator usually has a large dimension to ensure that the heat dissipation capability. In order to enhance the heat dissipation capability, the further reduce the dimension of heat dissipator as an active micro air cooler is designed and realized. As shown in figure 6a, the active micro air cooler can generate high-speed air jet flow. Such high-speed air jet flow can drastically reduce the thickness of laminate flow layer, enhance the local heat exchange coefficient to the heat. In addition, the air jet flow generated by micro air cooler is unidirectional, where cool air is sucked from rear of the micro air cooler and pumped out from the nozzle. The micro air cooler works like a fan, generating the net air flow. This ensures the air jet flow of heat exchange is always good, and the heated air can quickly leave the heat dissipated to the environment. In figure 6b, here we can see the experimental data of micro air cooler. The micro air cooler can generate the air jet with velocity as high as 11 meters per second. The output flow rate is also high, which reaches 0.3 liters per minute. Such high air jet velocity and flow rate could help the heat rapid dissipate to the environment. Now let's talk about what's next. The development of more sophisticated and innovative technologies for designing and manufacturing microfluidic systems is the need of hour, and it can promote commercialization of microfluidic devices. That's why we need to have a good thermal management system in order to further innovate in the field of nanotechnology. So, the conclusion. In conclusion, microfluidic heatsink has a very good capability. The embedded sensor helps to reveal several unaware phenomena together with the highly efficient micro pump, micro air cooler, and the microfluidic thermal management system shows great potential in electronics thermal management. Thanks. If you have any questions, you can find me at Cheers.